All right. Hello, everyone. Howdy. So obviously the test is this Thursday, which I think we're all very acquainted with, hopefully. For funsies, the test, so just to remind you all, it's 24 multiple choice instead of 25. The only reason it's 24 is I just couldn't think of another problem that was worthwhile asking, so I just made it 24. Last test said 25, whatever. The free response, remember there will be 5 free response. You will pick 4 of them. And 4 of the free response, one of them's on DC circuits, one of them's on sources of magnetic fields, one of them's on forces due to magnetic fields, one of them's due to the Faraday's law, and then the last one is like kind of a combination of a couple of them. Doesn't mean it's like more complicated. The 2 pieces you use are fairly straightforward, but yeah. The 5th one it does have to do with magnetic fields because that's what we spent most of the time on. So, but I used a couple of the concepts together. Yeah, I'm optimistic. I think it'll go well. I've double-checked it. Your TA and LA have double-checked it for typos. Does not mean there's not typos, but, there should be. If there is any, they should be minor to non-existent. Fingers crossed, non-existent. They've also looked it over and deemed it appropriate, difficulty-wise and length. So, if you don't like it, be angry at all of us, not just me. But I think it'll be, if you've been doing the practice, you should be good to go. Nothing if you've gone through the problems, you will have seen versions of the problems, like none of it should look out of nowhere. That's always when I design these things. A good rule of thumb, any problem I give you, I've given you at least 2 versions of that to practice. That's a good rule of thumb with any problem I'm going to give you on a test. So, and I can point to whatever those problems are as well. I'm very, very careful on that. All right, joke time.
Yeah. Refusing to go to the gym is a form of resistance training. Also, I have a quick announcement. I run the Grad Student Society of Physics and Planetary Students, and we're doing a little tailgate before the space game on Friday. So if you're around at like 5:30 p.m., starting then, we're going to have a table set up at the Arboretum right next to the physics building. So hope to see you all there.
Nice. All right. So, test to review. This has been posted for a while, so this is available. Open it, whatever. As always, after this, I'll post it with all my writing scribbled all over it. Be a grand time. All right, so something you're going to notice is a lot of these slides are just kind of the equations. And then, I'll talk about the equations. But this is just a good strategy for studying in any of your all STEM classes. Look at the formula sheet. The formula sheet is effectively a summary of everything you learned that entire semester. As weird as that sounds, the formulas are compact, logical expressions that if you understand what they mean, if you can read the sentences, they're little sentences, they tell you the concepts. So like P equals IV is the power in a circuit is given by the current in the circuit times its voltage. So anyway, as you kind of go through this is a great strategy for this class. This is a great strategy for every one of your classes. Look through the formula sheet, and if you don't know what an equation is, you should probably look into that and try to find problems that use that equation. I think there's maybe one equation in the formula sheet for this class that might not be relevant. I see if I removed it or not, because I think I did include Biot-Savart's law, which the reality is I never have you do Biot-Savart's law. Let's see. I did keep it in here. This is the only equation you don't need to really bother with, but every other equation on here you have used at some point. So like test 1 used basically every single, that's actually one of the ways I design tests, is I make sure every single equation is used at least once somewhere in the test. Test 2, yeah, every single one of these equations is going to show up somewhere in the test. I guess one exception is here you have the charging and discharging. We'll talk about those real quick. Maybe only you use one of those, one or the other kind of thing, maybe not both. But yeah, the rest of these, force of a moving charge, force of a current carrying wire, centripetal force, things go in a circle, Ampere's law, straight wires, arc of wire, solenoid. Again, we're going to see all these. This is how I make the review as well. Is I just copy and paste the formulas and then talk about them because they are a summary. This entire section is everything we're going to learn in the entire class in a summarized way, which is kind of wild. Equations, right? They're so good. All right, so P equals IV. There is one equation I forgot to put here, but it shouldn't be like a surprising one. You know, you do need to know V equals IR. That should not be like a surprising equation to you all. That is relevant. And V equals IR, P equals IV. P is the power in a circuit. So if you buy a 10-watt light bulb, that means every second it's using 10 joules of energy. Now, when I say using, I don't mean destroying. I mean you're converting electrical energy into something else. Light, heat, whatever that appliance might be. In the case of a light bulb, it's mostly light. This P equals IV and the V equals IR, you can put them together. So you can rewrite this as P equals I squared R. Where did that come from? I just took this and put it where the V was. And then boom, you got another expression. Or you can have P equals V squared over R. It just comes from using Ohm's law and rearranging. So you all can do that exercise. On the test, I only give you V equals IR, P equals IV. The other two are pretty easy to derive. Put them on your note card if you want. All right, resistors in series and parallel. You need to know how to add them in series. You need to know how to add them in parallel. You need to know what series and parallel even means. And we're going to do a practice problem later on to practice that. Series is easy. People didn't have no problems with series. Parallel is the one that throws people off. Remember, parallel voltage is the same. Series current's the same. Great. Then we got Kirchhoff's laws. The sum of voltage in a loop is 0, meaning if I start somewhere in a circuit and I swing back around to where I started, my height didn't change, quote, height. So we're going to practice that using this picture in a little bit. The other one is the junction rule. The current that goes into a junction must equal the current that comes out of a junction. So let's just make a quick example of that. I didn't make one here, but it's really easy to make one. All right, that goes in like this. That goes in like this. Sure, let's make that one go out. Let's call I1 2 amps. Let's call I2 3 amps. You know what? Let's just do this to be funky. And the question is, what is I3? All right, try it. You got this. It's pretty. Do the junction rule with that. Yeah.
Just to be sure, a battery, like on the circuit diagram, the bigger ones for hot.
Yes. Yeah, and we'll see that. We're going to use that circuit and do a practice problem with it. Yeah, in a bit. What goes in must go out. You might look at this and be like, but wait. Write out the math and see what happens.
Oh, yeah. I was thinking about
All right, so let's just do it. IN equals I out. So I1 plus I2 plus I3 equals 0 because they're all pointed inwards. Put in the numbers. 2 plus 3 plus I3 equals 0. So what does I3 equal? -5. What does that mean? It means I drew the current in the wrong direction. The current doesn't actually go that direction. Does it matter I put the arrow inwards to begin with? No, the math fixed it for us. So the current actually goes the other way. So when you get a negative current, that just means it flows the opposite way that you defined. That's fine. Now, again, I'm not going to do something weird like that in the test, but this was a particularly funky one just to show you all that. It's going to be relevant when we do these loop rules and things like that. All right, and then at the bottom, we have the charging and discharging for an RC circuit. What those functions say is they say charge is a function of time on the capacitor equals Q naught. This Q naught is the max Q. That is the maximum charge on that capacitor. And so the charge is some function of time equals that max charge times 1 minus e to the negative t over RC. Looks kind of like a weird equation, but it's a really easy one to use. Make sure you've actually practiced using it. You can test that this equation is correct. When you're charging it, so when I'm charging a capacitor, how much charge does it start with if I'm charging it? 0. Let's test that. When t equals 0, plug in t equals 0. You get e to the negative 0. What's e to the negative 0? 1. What's 1 minus 1? Oh, look, the charge is 0 at time equals 0. It matches what we expect. So this is one way you can kind of test these. Whereas when you're discharging it, how much charge do I start with? The max. Test it. Plug in t equals 0. When t equals 0, e to the negative 0 is 1. So at time equals 0, I start with all the charge. It matches. You can also do t equals to infinity. That's the opposite side. This is a very useful skill. We call these boundary conditions. Boundary conditions are the extremes. Any function you all have, if you kind of look at boundary conditions, you can determine how it's going to behave. If you can determine how it behaves in the very beginning of something and the very end at something, you can kind of determine what's going to happen in between. It's a very useful strategy. We do it all the time in physics. Boundary conditions are super, super important. Or limiting cases, I forget. Is that the right term? Boundary conditions? Okay, great. I was like, some reason in my mind I doubt that. All right, so let's actually start applying. Let's start applying these. I don't have any practice ones for RC circuits, but there's plenty in the problem set. Make sure you can do those. I can guarantee one of those equations will be used in the test. To that end, before I jump to the other ones, a very common question on these charging and discharging is where I ask you, how long does it take for the charge to reach 70% of the max, 30% of the max, 40% of the max? The thing that you want, so you should be comfortable doing those problems. And the reason I like those problems a lot is you don't actually need to know the max charge. If I say the time it takes to reach 40% of the max is cancel. Back to your all's chemistry class, you've done these problems when you had like a half-life problem. How long does it take for my population to reach half the size? It's important for y'all to be able to kind of do these kind of equations where it's written as some max times some function. You'll see those in other classes. I mean, you already have with chemistry. Okay, here's a circuit. You all need to determine how to turn that into one resistor. And that's going to take a couple steps. That is not a one-step process. So, try it. You cannot do this in one step. Oh, and all these have a resistance of R. That is not a requirement. They could have different resistances. But for the sake of quickness, I'm just going to say they all have the same resistance R. That is not, in the real world, they tend to have different resistors, but whatever. All resistors have a resistance of R. Just to make things quick and easy, not because that's how the real world works.
I'm thinking
Nice.
these three are parallel to each other, these two are parallel to each other, and this is in series with that. Okay, that's what I was doing.
So these are in parallel. So you can turn them into one resistor. Great, what you did. Now these ones are in parallel, and yeah, there's
because of this node here.
yeah, we call those junctions. Node is another phrase for it as well. If they have a junction or a node in between them, they're not in series. Yeah, the whole idea is in series there should only be one path. Like it's a one-way road. In this case, it's not a one-way road between these, so I can go this way or I can go this way. Yeah, so these ones are connected by the same wire on this side, and they're connected by the same wire on this side. In fact, these three are in parallel. Because they all are connected by the same wire at the back, and they're all connected by the same wire at the front. Their voltage is the same. Wire to voltage is the same. Yep. And voltage in that wire is the same.
These three are
Yep.
parallel
And those.
in series with these.
Yep. And because I did this morning, the answer is 5R over 6. I did not just solve that in my head that quickly. I did it this morning. So the trick with parallel, they need to start with the same wire and they need to end with the same wire. So you can have start of that wire or that. So this wire can be the two. Right. So let's just they all start with the same wire.
Oh yeah.
In specific. I know what it is.
In other words, so
they share the fire. They share their voltage drops the same wire. So we can color code it. Yeah. And the key here is just realizing what is purely in series and what is purely in parallel. Series is easy. None of these are in series. None of them in series right now. Once you start combining them, they'll start to get So, reminder to y'all with parallel, one thing that's helpful, parallels define that they start and end with the same voltage. One of the tricks I taught you all was like color coding it. So everywhere where a wire is, the voltage is the same. The voltage only changes once you go across a resistor. So everywhere on that red wire, the voltage is the same. Everywhere on this purple wire, the voltage is the same. Everywhere on this green wire, the voltage is the same. Voltage is the same everywhere on a wire. It only changes when you go across a battery, a resistor, capacitor. You have to go across what we call a circuit element, some functional piece in it, not just a wire. So now you just got to look at this, and you can hopefully see that I have two sets of parallel here. Two sets of resistors on one side. So these resistors are in parallel because they start and end with the same voltage. And then if you look at the ones on the right side, these three are actually in parallel because they start and end with the same voltage. Saves you a step. The key to parallel does not mean that they physically look parallel. That's the habit that a lot of people get in. Sometimes they look parallel, sometimes they don't. You need to understand that this voltage is the same across them. That's the greater idea.
even if a resistor has more resistance.
Yeah, even if they have more, we don't actually care about these resistance values.
Okay, so the change in resistance would be the same.
The change in voltage would be the same. Yeah. Voltage. Yeah, the question was a great question. So the voltage is the same even if they have different resistances? Yes. We don't actually care what these resistance values are for that rule. Parallel doesn't depend upon what the resistance values are. I could have this resistor be 1,000,000 ohms up top, or 1,000, and this one could be 50, and they're still in parallel. Why? Because their voltage drop is the same. That's how we define series and parallel. Now, we do need to know the resistance values to actually combine them together. So I made it simple. I just said they all have the same R, just to make math easier. So these first two resistors, let's call them 1 and 2. Let's call this one 3, 4, 5. So if I want to get R12, we're going to do 1 over R plus 1 over R. And that's going to, through the power of math, going to be R over 2. In parallel, you always get a smaller resistance than the smallest resistor. In parallel, you always get a smaller resistance. Why? Think of these like roads. I don't care how, if you have a 6-lane, let's just say a 3-lane road and then a little bike path, if I kind of treat that like one big unit, the bike path helps. The bike path does reduce the resistance, makes it easier. In parallel, it's like a bunch of roads, and you kind of smash them together. I don't care how tiny that road is, it helped. No matter how thin that road might have been, it's going to make things go smoother. So in parallel, it's as if you took a bunch of lanes together. In series, you took those roads and put them one after the other. You made the road longer. That makes it harder. Whatever. All right, so great. That's that one. R3, 4, 5 is going to be 1 over R plus 1 over R plus 1 over R. That's going to equal R over 3. So we turn this into 1. Now, generally, I'm doing this a little. I generally recommend only combining like one group at a time, but as you get better at this, you can do groups together. Generally, I don't advise this, but like for the sake of time, I'm going to do it, which is maybe not the best practice. Whatever. Turn them into one. It still starts with the 5 volts. It still ends with the ground. Now they're in series. Give you all a few moments if you haven't done it already. And my follow-up question to you is, if you've already solved this, find the current through the net resistance. See if you can do that. You know what? I'll give you 2 questions. Find the current through the net resistor. Find the power through the net resistor. Those are common things you can do with this circuit. All right, so you just add them together. Now, be careful. This is going to be obvious. You'll be like, so R over 2 plus R over 3 is not R over 5. You may be like, obviously that's not the case. I'm not an elementary school person. Look, when it gets a test, simple math things go out your brain. I know how this goes. Just be careful on this, y'all. Remember when you're adding fractions, least common denominator. I've been walking for 33 years. 32? I don't know. I don't know when I started walking in my life. Slightly age. I've been walking for a little over 30 years now. I still trip every now and then. The same happens in math. So how do you make sure you don't trip? You just be careful when it really matters. If I'm near a ledge, I'm going to be really careful on my steps. On a test, be really careful with your math. All right. If I said find the current, remember V equals IR. In this case, I gave you the voltage for some reason. So we can do things with that. Yeah, my hand touched the things. So the current here is going to equal oh, it actually ends up really nice. 6R. That's my current. 6 times 5 is 30. Divided by 5 gets me back to 6. The 5's cancels. Another way you can see that.
Isn't it 6 over R?
Could be, if I did my math. Yeah, 6 over R. See, that's what happens when you do things in your head. Thank you. 6 over R. 6, yeah, the reciprocal. All right, and then, if you want the power, you got so many options. You could do PIV, you could do V squared over R, you could do yada, yada, yada. So, in this case, it equals 30 over R. So, this is one thing these problems could do. Another thing I could do in this problem is I could say, what's the current through R12? I wouldn't be as mean to say what's the current through R1 because that just requires too much time. Rule of thumb it takes too much time. Rule of thumb on this test is if I give you a free response, and this is kind of the level of a free response complexity-wise, if I give you a free response, you should be able to solve it in 4 lines or so, 3 or 4 lines. If you don't believe me, look at test 1. Look at the solutions of test 1. You'll notice all the solutions were basically done in about 4 lines. If you know what you're doing, they don't actually take that much. What I'm testing is, do you know what you're doing? Do you know the right equations? And then can you actually use them appropriately? And might have a couple steps involved and things like that. So, great. All right, next one. Oh, do I have the ghost? No. All right. Build the 3 loop rule. So I'm going to make this a little bit bigger because it's kind of small here. So normally if you were an electrical engineer, what they would do is they would give you this circuit and they would say, find the current through the 3 ohm resistor. And that would be the question. That just takes a little while, more time than I want to spend on these problems mathematically. So I found an in-between where I just said build the loop equations. Now, for me to check that you're building the loop equations correctly, I will define the directions of current. So like in this problem, I say I2 is down through the 3 ohm resistor. So we draw that in the picture. I3 is down through the 20 ohm resistor. And I1 is down through the 5 volt battery. Is this actually the directions of current? No. But we just pick random ones and it lets us solve it. And if you all remember back to the first thing I showed you, the first little problem we did, If we pick the direction of current wrong, you'll just get a negative value, and that fixes itself. This is a very normal thing to do, doing these Kirchhoff's laws. And then I even tell you the direction of the loops. The direction of loops just determines whether everything's multiplied by -1 or not. You'll see what I mean to solve this. So, try it. Get the 3 loop equations, get the 1 junction rule. You'll see that, I told you that these currents, are they the right direction? And I told you I know they're not. You'll see when you build the junction rule that clearly one of them has to be wrong. And that's okay. The math would fix it if we actually did the math.
Against it. You got it, right?
Yeah.
So your first step is drawing where the loops even are. And in this case, we're going to draw them counterclockwise. Not because that's the best way to draw them. That's just the way I specified.
This direction, though. Counterclockwise? I know, but the loop is on this way, right? Wait, and still try that.
What makes you say?
Because it's wrong, it says counterclockwise.
Okay, then you're right.
Okay.
I'm so sorry.
No. I just can't remember because it doesn't matter.
Yeah, I just for me in my head I always go like with it.
Yeah.
But yeah.
Okay. Then I think I did it right.
I see that now.
So we're doing it for like it doesn't matter what you do. Sorry, the direction of the current.
Just the direction of travel.
Okay.
You do care about the current.
For the voltage I'm across the battery.
Oh, not for the battery. Sorry, not for the
Okay.
battery. Batteries are, they're speed.
Yes.
Whereas current, resistors kind of go like water flowing down. Current will go hard down.
The first one is that. I don't know. Is this your the right half of it?
Oh my gosh. Do.
The whole one? I didn't know how to do that one because.
And then I can show you.
Like, do I just ignore? Oh, I just ignore it? Okay.
All right, so there's your 3 loops. So how many circles can you draw? 3 circles.
Like this. Now, your first one.
Oh, yeah, she's not.
So normally a voltage draw.
So I just like ignore it if I'm doing
Yeah.
it.
All right, so I'll do the blue loop for you all. So we pick some spot. Remember, the trick to this is imagine you're walking through the circuit, and you have to ask yourself whether I'm walking uphill or downhill as I go through each circuit element. You pick some random spot to start in the circuit. Doesn't matter where. I'm going to pick there, and I'm going to make my way around that blue loop until I get back to where I started. So I'm going across this, and again, I go counterclockwise. Why? That's just the direction I picked. It doesn't actually matter too much. All right, if I go from the big end of a battery to the small end, did I go up in voltage or down? Down. The big end is positive. The small end is negative. That means I went downhill. For batteries, you don't care about the direction of current. You just care about whether you started at the big end or you started at the small end. And then, in this case, I went down. All right, then I hit the next battery. Again, I'm going counterclockwise. I go from the big end to the small end. So I go down again because that's how batteries work. And then I keep going. There's a wire down here. Don't care about it. I get to the resistor. The way we do resistors is think of current like water flowing. Does water flow uphill or downhill? Downhill. So if the current's going downwards, it's going downhill. If I'm walking opposite the way of water, I'm going uphill. So this is plus 3 times I2. And then all this, I get back to the beginning and it's 0. So that's the idea. Now, if you actually solve this, we find that I2 is in the You can actually solve for I2 and you get a positive number, and that would say, great, we did a good job with I2. It's actually positive. I1 and I3 are the wrong directions, but we'll find that later. All right, so I'm just going to chuck the other equations here, and then I'll give you all a couple moments to figure it out for yourself why or why not. But I'll at least put the answers in case you already have them. But keep working on them if you haven't. Oh, you did. Okay.
I don't know. Don't you want to get switch? On the exam, it's like I don't know. Oh, it's all the way.
Okay. See now who's well, wait. Yes.
All right, there's all four answers. So just, I'm actually not going to even solve out the rest of them. Those are good practice ones for you. Practice that uphill, downhill. The answers are there. I guess I'll say it out loud. And this one, we're going counterclockwise. You're going the direction of current, so you're going downhill. When you go through the other resistor, you're going uphill. So first is minus, next is plus. Big old loop around the outside, down, so it's negative, down, so it's negative. Then you hit this resistor, you're going opposite the direction of current, so it's positive. And then this last one, the junction rule. I have two junctions here, and it doesn't matter which junction you pick. It works out fine either way. Pick this top junction. This top junction, let's draw the directions of current. I3 points away from it. How do I know that? If I3 points down on this side, it has to point, it's a one-way road. So for it to be a one-way road, current must flow away from that junction. I2 also points away from that junction. You can see that more easily. I1 also points away from that junction. They all point away. So I1 plus I2 plus I3. So if you were like, but wait, shouldn't it be current in equals current out? Great. There's all my currents out. It's the exact same expression, just on the other side. If you did the bottom instead, you have I2 going in, you have I3 going in, you have I1 going in. Oh, look, it's the exact same expression. Just it depends on what side you put the things. I1 plus I2 plus I3 equals 0 is the exact same thing as 0 equals I1 plus I2 plus I3. They're the same equation. Great. So those are the things. And now so it would now be possible to find I2. We would find that I2 is positive, which means we got the right direction of current. If you solve this, you could find I3. You would find I3 is also positive, so we got the right direction of current. I1, you'd find the direction of I1 from that last equation, and you would find that I1 is negative. I1 does not go the direction I put. And that's okay. We find that from the math, and this is what software does with circuits. This is how it analyzes circuits, is these two expressions. Cool. All right, so that is DC circuits. The only thing we didn't practice was RC circuits, but, do practice those. I guarantee you there's one on the test. I know this because I made the test. All right, right-hand rules. Here's a nice little summary slide of all the right-hand rules. There is two categories of right-hand rules. There's right-hand rule 1 and right-hand rule 2. 2.5 is just a variation on right-hand rule 2. The reason I call them 1 versus 2 is the purpose, right? And this is a question I get all the time. Which one am I supposed to use? It depends on what you're trying to do. If you want to find, right-hand rule 1 is force on a moving charge. That's the purpose of right-hand rule 1, is force on a moving charge. What's the purpose of both of the right-hand rule number 2s? It's to find the direction of magnetic fields due to current carrying wires. First rule is for force. Second rule is for magnetic fields. Now, the first one does have magnetic fields in it, but that's the main kind of distinguisher. So right-hand rule number 1, you put your fingers in the direction of V /current. positive charge is a moving positive charge is the same thing as a current. That's what current's defined as. Then you need to be able to swing your fingers towards B. And your thumb then gives you the direction of force. If this was a negative charge, the force is opposite. Remember, negatives always do the opposite. Everything I teach you is about positive charges, and then I tack on negative charges do the opposite. That's why they exist. That's how we identified they exist. So just so you know, to model this, put your fingers to the right, swing them towards B, your thumb points into the page. I've mentioned this several times, but I want to mention it again. Right-hand rule number 1 is not exclusive to this class. It's not a rule I'm just teaching you that's only useful for this class. Right-hand rule number 1 is the technique to solve any cross product you ever see in any class. So, where did this right-hand rule come from? It came from this, QV cross B. So given some velocity vector, given some magnetic field vector, I can find the direction of the force vector from this cross product by doing right-hand rule number 1. In physics 1, you may or may not have learned about torque. Torque is also a cross product. How do you find the direction of torque? Right-hand rule number 1. And there's many other cross products you'll likely learn in your future classes. Any cross product you all ever learn moving forward, if you want to find the direction of, just to make it a general expression, let's say C equals A cross B. If I want to find the direction of C, I put my fingers in the direction of A, I swing them towards B, and my thumb points in the direction of C. This is true of any cross product you'll ever learn. So just to kind of convince you that this is a useful thing to know how to do. Right-hand rule number 2 is exclusive to this class. So, that one is, and that one's actually easier. So in this case, if we have a current carrying wire going into the page, you put your thumb into the page. My fingers show me that I make a clockwise circle. If I want to find the magnetic field above the thing, I draw the tangent to that circle. That's kind of the first technique. So just to show you all that with the whiteboard over here, make sure you all practice this yourself. This is about 30 to 40% of the test. Thumb in, yay, my finger makes a clockwise circle. If I want the magnetic field at the top, the tangent line to that circle at the top is to the right. If I set it on the bottom, the tangent line is to the left. If I set it on the left side, it's up. By understanding it's a circle, you can find it anywhere. The simplified method is put your thumb in the direction of current, keep your hand flat, point your fingers to the point, and your palm points the direction of the field. That's kind of the simplified way. And you can see as I kind of move, if I want to find it top right, great, now it's down to the right, and you end up tracing a circle. So it gets you there as well. Make sure y'all can do that. This is a nice little summary on that. Something I'm not going to do, but that you can do with these also work backwards. If, for example, I said I got a current carrying wire, it's either pointed into the page or out of the page. The field above it points to the right. Which way is the current going? You could do right-hand rule backwards. That's why I made this how process. I didn't make it step 1, step 2, step 3. I made it bullet points because these are reversible. You can go backwards with these things. And actually, right-hand rule 2.5 is a great example. We've done that a bunch of times. Right-hand rule 2.5 is a shortcut for an arc of wire. And there's 2 ways you can do this. For example, say in this problem, I say the current's clockwise. Which way is the magnetic field? Put my fingers clockwise. Inside it, the magnetic field is into the page. What if I said I had a loop of wire and I said it makes a field into the page? Which way is the current? Put my thumb in the direction, it's clockwise. It works both ways. All these rules work both ways. It's important to remember that. They're not just like they always give you force or whatever. I am not going to have them go backwards in the test. I haven't given you all enough example problems or like any going backwards on or doing other things, but you can. They're not too bad. All right, equations. I already wrote one of these. There's the other one. The force in a moving charge is given by QV cross B. You need to remember that the cross product is just equal to the magnitudes times sine of theta. If it's a current carrying wire, it's L times B times sine theta. If your magnetic field is not uniform, or if your angle is not uniform, you got to integrate. Why? Each tiny piece of the wire will experience a different force. If there's a field that varies in space, it's going to cause different forces on different parts of the wire. how do I add up the contributions of the forces on every tiny piece of wire? That's what an integral does. And that's a skill that I keep trying to remind you all of. If you can break a problem into an infinite number of small pieces, an integral will give you the whole picture. That's why integrals are useful. They're incredibly useful. In your all's future classes, they will become as ubiquitous as algebra. Maybe they might not actually have you do the calculus, but it'll be there somewhere. Without it, we just can't do as much. Yeah.
Theta is the angle of B and B, right?
Yeah, it's a great question. I'll put that here. Theta is the angle between the velocity and the direction and the magnetic field. So theta is between V and B. So, there's a question. We're going to use that picture on the bottom in just a second. In a uniform field, charges will make a circular path. Direction of circle, we got to do right-hand rule. We're going to practice that in just a second. Yeah.
What's the difference between the two equations?
Yeah, the first one is a single point charge flying through space, or like a particle that's charged flying through space. The second one is a current carrying wire, which is effectively a whole bunch of them traveling through a wire. Think of it as the difference between a single car versus a highway filled with cars. The first one is just a single car traveling. That's that single point charge. The second one is a highway filled with cars. That's what a current is a bunch of moving charges. All right, I want y'all to look at that bottom picture and determine what the angle is between V and B. Approximately. Think about it. You should be able to get very, 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 very close to the right angle. You have all the information you need to find the angle in that picture. Yeah. All right, so in this picture, B is pointed into the page. B is at some angle up to the right. So what's the angle between those? 90. It's very tempting to look at that picture and think that B is at an angle to B, because it's like we're not measuring with respect to the x-axis. Don't fall into that trap. B is into the page. V is upright. They are 90 degrees to each other. If you looked at this from the side, it would be very hard to draw, so I'm not going to actually. This is just hard to draw. You just have to realize into the page and that are 90 degrees to each other. I can show you with my arms if you're at home. Sorry. All right. I got two questions here. The first one's easy. The second one is, we'll see how you do. It's not hard, but it's going to test if you know something that most people overlook. It says find the direction of the magnitude of the force. If the velocity is 3 meters per second, B is 5 millitesla, and I forgot to put what the charge is. Find the direction of magnitude of force on a proton, moving proton. If V equals 3 meters per second, B equals 5 millitesla. And the second question is a really interesting one. That's the one I'm going to be curious how people get right. What would be the path of the particle over time? As in, draw its path on your paper. That's what I'll be kind of looking around to see. And its path over all time, not just immediately, over from t equals 0 to t equals infinity. What's that path going to look like?
Yeah.
But it would make it.
Yeah.
Alright. I don't. I stole his answer.
You get that answer 2.4.
2 point.
Great. I stole his answer.
Oh, nice.
He had the right path written down, so I just chose it.
Now, what'll happen to us right? So, B is the same.
Yeah.
So over time, how it's being formed up.
So that's V1.
It was always in the
After this, I don't like you. Okay. It's good. It's always changes.
Yeah, so we will need the force at this exact moment. So which way is the force on this exact moment? Yeah, and 90 degrees, that's right. So what's that going to cause the velocity? Which way is the velocity going to be? And then when it's this way, the force is still the other way. This way, the force is going to be forever and ever and ever and ever and ever and ever and ever. Yeah.
So it's going to affect the velocity. So it's 4. Stay at that 9 degree. The force is pointing to the center of what would be the circle. It's just like the
All right. So the first part is really easy. All right, so first part's really easy. That looked good. The second part, I was really encouraged by what I was when I walked around. So to find the path, we do need to find what's going to happen immediately, and then we got to keep doing it. So immediately, what way is the force going to be? It's going down to the right. The field is into the page. Which way will the force be? Up and to the right. Up and to the right. If there is a force up and to the right, what's that going to cause the velocity vector to do? It's going to cause the velocity vector to bend kind of upwards because that force is kind of upwards. So a little bit later, the velocity will now be to the right. You know, it will have traveled downwards. Let's draw it down here. Do right-hand rule again. The force is going to be this way. This force is going to keep pulling that velocity vector. And so what ends up happening is it pulls it now this way, and then up here, you know, it's going this way. And yeah, if you have a force pointed perpendicular to velocity, you always get this result. You get a circle. If the force is perpendicular to velocity, you always are going to get a circle. That's just a useful kind of, I don't know what else that pops up in. Anyway, you all can kind of figure all this out. It's a counterclockwise circle, and it will stay spiraling in that circle forever and ever and ever and ever and ever. Now, someone had a great question, and they mentioned on the slides there was like a helix. I'm not going to ask any questions about helix. If you're like, what's a helix? So a circle is a circle. A helix is a circle that like moves forward, almost like a slinky. A slinky is a helix, something that not only goes in a circle, but also, you know, moves a little bit in one direction. If this had a velocity at all that pointed into the page or out of the page, even just a little bit, it would make a helix. It would not only make a circle, but it would keep moving in the also direction parallel, and it would like spiral into the board in the circle. That's a helix. This is the Earth's magnetic field, and charged particles, they get trapped. They spin around the Earth's magnetic fields, and they kind of follow it along. Great. I'm not going to do any helixes on the test because they're really hard to write problems for. All right. This one I like a lot. I have a current carrying wire. It has current I. It points in the positive x direction. What is the magnitude and direction of the force of the wire between the points x equals negative a and x equals 0 if it's in a field given by x 8x hat minus 3x squared y hat? What I want you all to do here, first step, draw a picture. Draw the current carrying wire. Draw the magnetic field. And the fact that this field is written in vector notation, I recommend you draw the components of the field. Draw them as two separate pieces. Draw what the x component of the field looks like. Draw what the y component of the field looks like. Don't draw the net magnetic field. Actually draw the vectors for the components. You'll see why when you do it. For now, it's a trust me situation. Yeah. Draw a picture. If your picture is good, you're going to have a great time. If your picture is bad, you're going to have a bad time. It's pretty easy. Yeah. Yeah, the solution is pretty simple. Because it's parallel to the. So I'm not going to do them like this in the test. Future semesters, I should put more of these because I thought I was like, oh, this is simple enough for them to be able to do it. But I didn't give them enough practice on doing versions like this, so I'm not going to do it. Yeah, that's fair. Yeah. Alright, so as I go around,
When it feels water. Yeah. Well, yeah, it's in terms of that. It's just pointed in. That's what I use.
You need both. You need both.
You started
Yeah, I like it too.
So I need some arrows in your magnetic field. Draw one part of it that's in the x hat direction. Draw one part of it that's in the y hat direction. I see what
I have negative k hat. So when you actually do it, it will tell you exactly like which direction it is. Nice. I prefer doing that because they're not think about it.
I mean, that's how you most of it, you know.
Right. You actually do it.
But just because, like, I think they're arrows.
Because
Yes.
Yeah.
Alright, draw these to the right.
You said it's conventional.
It's just one that's required for this class, right?
So that means every
Okay.
wire
Yeah.
is magnetic field.
But it's like most of
Now,
them.
if
If
there's
there's a specific convention, Everything is a coordinate.
So which way is the
Yeah, because I see you were saying.
If like in the y hat direction, so it is either up or down.
You were like a sandwich.
only the Y.
Exactly. So do it if you had never
Yeah,
seen it.
right.
So y always points up or down. So if my x is my y component of the field points down. Now, the strength of it varies. It's gonna go y and when you're at y, when you're at x equals 0, that is x equals 0. So you do want to have like your or x equals 0. But yeah, you got the right idea. As you go positive x, it gets bigger, but as you go negative x, it also gets bigger. All right, so let's draw this picture, y'all. Something helpful is anytime there's coordinates, you should probably draw a nice little coordinate system. It's useful. So that's my first thing, and then I'm going to draw my current carrying wire on this. Now, unfortunately, it's got to be right on top of it, but whatever, that's fine. Carries current in the positive x direction, everywhere, forever. Keep doing that. I didn't specify this, but we're going to assume this thing's on the y-axis. Or it's directly on the x-axis. I don't think anyone questioned that, but now that I'm drawing it, that is not specified. You see the challenge of writing problems, so many things to consider. All right, now I'm going to draw my fields. Let's make them purple. I need to draw two fields. I need to draw the field in the x direction, the x component of it, the y. I'm not going to combine them. You're going to see why we don't combine them as I draw these. So, at this point, what's the field? At x equals 0, what's my field? In the x direction. 8. What about when x equals 1? It's 8. It's 8 everywhere. Everywhere in space, the x component points to the right. You might be able to see why this is useful to draw this way in a second, if you haven't yet. My y component of the field, which way does that point? It's the y hat. Y hat either points up or down. That's the definition of the y hat vector. Now, when x equals 0, how big is this vector? 0. When x equals 1, what is the value of this? -3. So it's going to be a vector down. So as I get more and more positive, my field points down. What if I'm in the negative x coordinate system? What if x equals -1? What does that look like? It's still negative. This was purposeful to make our life easy. The field points down everywhere. Okay, why am I doing all this? If you all remember, the equation for the force on a current carrying wire, I'm actually going to write it this way first and then take a 180. This is the equation on the force on a current carrying wire. I have the current, I have the length of the wire, I have the magnetic field, and I have the angle between the current and the magnetic field. Here's the problem. My B is not a constant, so I can't just use this equation because B is not a constant. I can't just put it, what's the value of B? I have no clue. It depends where I'm located. So this is why we have to do the integral. Because the B varies based on where I'm located. So I need to find, what I'm pretending like I'm doing is I'm going to find the force on a tiny, tiny, tiny piece of this wire. Then I'm going to find the force on another tiny piece of the wire. And another tiny piece, and another tiny piece. And if I add all those up, I get the total force. That's what an integral does. An integral adds up the force on a dl is a tiny piece of wire. All right, now, build this integral. You all need to find theta. That is the angle between, okay, we'll do that one together real quick. What's the angle? So something note here. I have two magnetic fields, one in the x direction and one in the y direction. If my magnetic field points in the same direction as my current, what is the angle between them? So we don't care about the x component of the field. This is why we drew the pictures to help us see this. I'm not going to give you all a problem like this where it has both components. This is kind of like a bonus one, just to show you all this idea. Every practice problem I've given you all with this, I just gave you one component. So if I give you one like this on the test, it's not going to have an x and a y, just to so you don't get scared about this. But I thought this was a cool point to make. This problem is effectively saying the magnetic field is negative 3x squared y hat. Find the force. The x component didn't matter at all. All right, great. Now set up that integral. Find the angle between the current and the magnetic field. And set up the integral, solve the integral, and don't forget you need to find the direction of this force. You don't just need to find the value of it, you also need to find the direction of it. Between the points x equals negative a and x equals 0. I'll write the answer in a little bit. It's such an easy answer that I don't want to write it right now. Here's what
I think I thought it was my professor said this. Because I'm sure that you some of the parts Yes.
Do you know when Thanksgiving break starts?
I think we're Wednesday.
Thank you.
You know,
Yeah, we have. Wait, even better.
I don't. I was not. I know there's no class. Oh yeah. Veterans Day. Not here.
I was like, maybe 6
Yeah. I want to do that. Space
Yeah.
All right, we're integrating over the wire, not over the field. We're finding the force of the wire. So what am I going to change dl to? Dx. Then I'm going to put the field in here. The field is, now, something I forgot to do here. I didn't do a good job of this. Remember, this is magnitude. If you're like, why is it magnitude? The same reason the one above it. It comes from the cross product. These are magnitudes, so do not put that negative in there. So it's just 3x squared. What is the angle between them? 90. One's to the right, one's down. 90 degrees. Side of 90 is 1. Yay. My bounds are from negative a to 0. And last thing, there's always a step you all need to consider. I am adding vectors. I am only allowed to add vectors if they all point in the same direction. So why am I saying that? We need to find the direction of forces before we actually do this integral. If I pick a couple pieces of wire, a couple tiny DLs, call this DL1, call this DL2. What is the force on DL1? Point your fingers in the direction of DL, swing them towards B. Which way is that force? Into the page. So this is DF1. What about the second one? Oh, it's the exact same thing. It's also into the page. Why is this an important step for us to do? if they both point into the page, I can just add them. I don't need to break it into X and Y. There is no components I need to worry about. When you all are adding vectors, don't forget to do that. So this answer comes out really easy. It's x cubed from negative a to 0. So you end up just getting IA cubed. Oh, and which way is that force? Out of page. Into page. Alright, so there you go. You all should be comfortable building these integrals, drawing these pictures. Should you be comfortable working with a magnetic field that has 2 components? No, don't worry about that. I'll just give you 1 component if I give you a problem like this. Future semesters, I'm totally going to give them 2 components, but I didn't give you all enough practice, so I'm not going to make you do it. Alright. Halfway through. Now, what makes magnetic fields? There's wires. Current carrying wires make magnetic fields. And I gave you all 3 geometries. I gave you an arc of a wire. I gave you a straight wire. And I gave you a solenoid, which is just a bunch of loops that makes a slinky. These pictures are super useful. And there's, I guess you could call this a typo. I should have called this A. It's one thing to have the equation. It's another thing to know what the variables represent. I have worked with enough students at this point to realize that these angles throw people off. So we're going to again practice that, but this is a skill you all need to be able to do. That's first one, arc of wire. Mu naught I over 4 pi a times theta. Theta is the arc of that wire. If it is a full loop, then that theta is 2 pi. If it is half a loop, then that angle is pi. If it is a quarter of a loop, then it is pi over 2. You know, whatever it might be, put that angle in radians. Radians are real, degrees are made up. When we plug in direct angles like this comes from the definition of arc length. You know, you can look at a full circle and you can see why it's 2 pi. 2 pi times the radius gives us the circumference. That's where it comes from. All right, great. So that one's actually not too bad. Generally, people do pretty well with that. The second one, man, that finite wire, this gets people every time. I have the picture here for you all. R is the closest distance from the point to the wire. Theta 1 is the angle between the leftmost point. It's that inside angle. Theta 2 is the rightmost point, and it's the outside angle. A lot of people make mistakes, and theta 2 they put as the inside angle here. Or what I even see people do is there'll be another wire, and they'll call theta 2 this angle. We ignore it, so we're going to do a practice problem in just a second, and we'll see if that happens. And that's okay if it happens. Better to happen now than on a test. Theta 2 is the angle between that dotted line and the horizontal, like the line lined up with that point. Now, something I've mentioned, but I don't think I emphasized enough, so I want to really emphasize it here. If the point is in line with the wire, B equals 0. And if you're not sure what I mean by that, I tried to include an example on this picture. Notice this point here is in line with the wire, this little dot right here. Everywhere on that dotted line I just drew, the magnetic field is 0 due to that wire. That is something you all need to know. Everywhere along this wire, whether you're off it, doesn't matter. If you're lined up with that wire, the field is 0 everywhere on that line. You can technically derive it from this expression. When you're lined up with this, so you know, if I had a wire and I said find the point here, and I did this whole angle thing, both angles are the same, and so they end up just canceling. So for example, in this case, the angle would be theta 1 is pi, theta 2 is also pi, so cosine of pi minus cosine of pi is 0. If you're like, how is that the case? If I picked a point that was slightly above this, it's a little bit easier to see. That's theta 1. Theta 1's that inside angle. Theta 2 is this outside angle. So as this gets flat, theta 1 goes to pi, theta 2 goes to pi, it cancels out. That's the proof. But yeah, you all can just remember the rule. If you're in line with the wire, the magnetic field is 0. We've used this to solve problems. And solenoid is easy. It's mu naught, capital N, I over L. That could be written as mu naught, lowercase n times I, where lowercase n is the turns per length. If you have multiple wires, if you have a really complex looking system, you need to break it into straight wires, arcs of wires, and I say solenoids, but there's no way I can draw a picture with a solenoid, so you're just not going to have to deal with that. Break it into straight wires and arcs of wires. Find the field due to each of those, their vectors, combine them together. And to see if this made sense, here's the problem for you all. I have a current carrying wire coming down from infinity, down to some point, then it makes a left-hand turn, then it goes down to infinity. I then have a loop of wire, and my question is, what is the magnetic field inside of that loop, dead center in that loop? I want to know the value of the magnetic field. I want to know the direction of the magnetic field. I want to know both. Break it into pieces. Break it into straight wires and arcs of wires. And then you can kind of draw each one by itself, find the field due to each one, and then go from there. It does not simplify. It kind of simplifying it takes a little bit of work. In my first class, I didn't simplify. I just wrote each of them, and I said, "This is good enough."
Yeah.
So what I'm going to be looking for on your all's papers, I'm going to be looking if you identified what the pieces of wire, how to break it into its pieces that you can solve. You can label them. Yeah, label 1, 2, 3.
Okay, I was like.
I just told you there's 4 pieces you should be considering. And then find the field to each piece. Find the field to each piece, both its strength and its direction. Hold on. And then once you have the 4 pieces, you can draw them separately off to the side, one at a time. Sometimes people get into problems when they try to use the original picture because they get mixed up with the other wires. When you're doing each piece at a time, you're doing exactly that, each piece at a time and ignoring everything else. Yeah.
Did you get the full loop?
So that's the easy one? Yeah. Yeah. Perfect.
I need to pull this out of my head.
I don't think it was. Yeah. That one.
Yeah.
I guess.
Sorry.
No, it's okay.
This one's not good for you.
I don't know if like that's because like I was confused.
So which one are you looking at right now?
So this straight line is like.
And I was like confused because like there's no, it's a
This is
finite
90
line.
degrees.
It is a finite,
Right?
so draw some dotted lines.
So the lines would be like that.
That's
but
45.
then, like,
That's one of them. Draw both of them.
Where does this one go to?
You draw
This is-
from the leftmost part of the what? So you draw
If this is
lines
theta
from the
1,
point.
then this
Yep.
should be
Okay.
And then if you just turn
Theta
this
2,
upside
right?
down,
Yeah.
you can draw theta 1 and theta 2.
Also, does it have to be in that orientation?
It
In like the up orientation?
it doesn't have to be, but if you want to
Technically,
match that
it should be
picture
on
that I
the
gave you on
side.
the last slide, this one right
So
here.
then,
It doesn't have to be. That'll help you.
So this. So this is
Yeah. Theta 2 is the
Two.
angle from
this is
the.
not.
Theta 1
sometimes
is
the
the
closer
angle
to people
from
up
the
the formation.
picture one, so that line
It's like
goes
2,
up,
4.
the wire to the point. So what is that one?
So 4 pi a times
It just
cosine
makes it
of
easy. So theta 1 that is the
minus
left.
cosine of 5
Yeah.
fourths. No.
And then this one is this.
3 pi 4. 3 pi.
90 plus 45.
Yeah. This will be 0. You know,
There you go. So that's the
There.
thought process. That's
Zero,
it.
zero.
You match it to the picture, and that's
But
how
there's
it's
two,
done.
it's double like
Oh, so just 3 pi. So root 2 unit over 8
All right, there's my 4 pieces of
for
wire.
that one. And this one.
So again, I'm gonna do exactly what I'm telling you all to do. I'm going to draw him off by himself. Current carrying wire 1 does that. If it's in line with the wire, what did I just teach y'all? That one doesn't matter at all because it's in line with it. Wire 2. Now, wire 2, I'm going to draw here. I'm going to draw the point. I'm actually going to do some things. How far away is wire 2 from the point? 2A. How long is wire 2? Also 2A. It's just useful to have these things kind of labeled. Now, how do I work with this? You need to make, the trick I recommend is making it look like this picture. Currently, it's upside down. So if you want, so what I'm going to do is I'm going to draw a line from one point of the wire to there and the other point of the wire to there. How do I label my theta 1 and theta 2? Look, just something helpful because it can maybe be hard to like imagine your head turning around. Take this. There you go. Now it's upside down. Now I can make it match the other thing. What does theta 1 correspond to? The angle between the left part of the wire and the dotted line I drew on the left side. That's theta 1. The left piece of the wire, that line, the angle between that and the wire, the inside angle is theta 1. See if you all can find theta 2. Boom, there's theta 2. Theta 1's easy. Hopefully y'all can look at theta 1 and say it's 90. Theta 2. You got some triangles involved that you might have to think about. It is a nice angle, quote unquote. It's on the unit circle.
No, where's this?
All right. So my hope is that you all, again, if you're not sure how to get this, there's a triangle that has equal sides. What's the angles on an equal side triangle? 45. So if this is 45, then this theta 2 is 135. Because that means this is 45, 45 plus 90, yada yada. So as I'm writing the magnetic field, I wrote the equation for a straight wire, mu naught I over 4 pi r. What's my r in this picture? What's the shortest distance between the point and the wire? 2a. Then I just put my angles in. Cosine of theta 1, that's 90. Cosine of theta 2 is 135. It actually comes out pretty nicely, so I get mu naught over 8a. Cosine of 90 is 0. Negative cosine of 35 is square root 2 over 2. All right, do wire 3 now if you haven't done so. Same process. If you need to, turn your head or turn the paper so that it matches. Draw the wire, draw your dotted lines, and then make it look like this picture. If you need to, turn your paper to make it look like that picture, if that's helpful. You can either imagine the rotation in your head, or you can just physically rotate your paper. Sounds stupid, but it works. And I'll give you all the answer to B3 just a second.
Have you taken a quantum class yet?
What's that?
Have you taken a quantum class?
No, but I wish.
You don't.
I know. Hey, I romantically speaking, I wish.
Yeah.
Being in the philosophy of the story.
Yeah, because we're cramming a bunch of quantum in 3 weeks, and it's been 5 years since I took the class, which makes me feel ancient. But
Yeah, it's been like 6 years since I took Calc 3, so I think 6 years. 24.
I'm 23.
Oh, really? There's no way. That's crazy. I thought you were like older than me.
Yeah, no, me too.
Yeah. No, I graduated high school in 2018.
I graduated 2019.
But I did take a good 6 years to get 6 or 7 years to get my degree. I took gap years and all that.
All right.
I just transferred you to last fall.
I need to be done. I'd like to have all my school done before 30.
All right, there's wire 3. What's theta 1 and theta 2? Theta 1 is this angle. Theta 2 is this crazy angle down here.
It's so weird to think about it. Or like visualize it.
All right, there's a magnetic field due to wire 3. Theta 1 is 45 degrees. Why? Because it's a triangle, you know, same sides. Theta 2 is the outside angle, not the inside angle. So that's pi, or 180. Pick your favorite. So great, there's that one. Now, something we have not been doing that we probably should have been doing is we should have been assigning directions. Wire 2, which way is the direction of this field due to wire 2? We should put that after our answer. So we got our current carrying wires to the left. So we point our thumb to the left. We then, you know, pick your favorite flat hand or curved hand. You point it towards point P, and it's going to point out of page. Do the same thing for this one. Thumb goes down. The points to the left, or depending on your perspective, the right of it. That also points out. All right, we only got one more field to do. Now, obviously, you can tell this problem's taken enough time. I'm not going to ask one that has this many pieces, but every single piece of this problem is something you need to be able to do. Can you do a finite wire? Can you do a couple finite wires? Can you do finite wires and a loop of wire? All right, so I got a loop of wire. It's going counterclockwise. This is our fourth situation, our fourth thing that we need to figure out. This is easy. Mu naught I theta over 4 pi times r. So this is going to be mu naught I times 2 pi over 4 pi r. Pi's cancel. One of the 2's cancels with the thing. Mu naught I over 2 r. Not r, a. Yeah, and which way does this magnetic field point? You do the shortcut, curl your fingers, points into page. Into page. All right, now, my question wasn't find the field due to every single piece. My question was find the net field. So what do you now do? Add them all up. This one's a minus sign. So we're just going to shove that up here. It's totally going to fit. So B net equals B1 plus B2 plus B3. B1 plus B2 plus B3. I'm just going to put the minus B4. B1 doesn't matter. Doesn't exist. Minus because that one's out of the page. So we get mu naught I over 8 pi a times square root 2 over 2 plus mu naught I over 8 pi a square root 2 over 2 plus 1 minus mu naught I over 2a. Sure, if you want to factor stuff out, feel free. Whatever, that's fine. It's good enough. Yay. So that's, again, I gave this problem because every piece of this problem is important. On the quiz recently, one of the most challenging problems people had was the wire bent to 90 degrees and find the magnetic field at some point. This is kind of a variation of that. There's lots of variations of this. I could have an entire square of wires or whatever. Make sure you all can work with finite wires, infinite wires, semi-infinite wires. That's what this is. A wire that has an endpoint and an infinite point is semi-infinite. All right. Cool. Fun. Ampere's law. This one's easy at least. Should be pretty straightforward for you all. It's an easier Gauss's law. It's easier because it only applies to one scenario. Draw a dotted line around your wire, intersects a point, solve for b dot dl. It always equals b times 2 pi r. Find I enclosed. If you have all of it, great. If you have none of it, great. If you have some of it, find the ratio. So reminder to you all, this whole ratio thing, we do this whole, the current density equals I enclosed over area enclosed, which also equals I total over area total. Then you can build a ratio of areas, and hopefully you've done this at this point. We're going to practice it on the next slide. So if you have it, you'll get a chance. If you got multiple wires, you care about them. If they're opposite directions, then one is positive and one is negative. All right, try it out. Wire carries a current of 3 amps, radius of 4 millimeters. Find the magnetic field at a point 1.5 millimeters from the center of the wire. This is not the easiest case, but it's the next easiest case, I suppose. Draw a picture. First step. Yeah. Yeah. Because it goes to infinity. That wire goes forever and ever and ever and ever and ever and ever. So imagine as this point gets farther and farther and farther away, that dotted line, is it going to get flatter or is it going to get Yeah, so let me borrow it then. Yeah.
It's smaller.
Yeah, that's the idea. As it stretches, that gets flatter. As this one stretches, say this side went to infinity, then theta 1 would go to 0. So yeah, it's all about inside and outside. I don't remember what the answer to this one is. I don't think I solved it. I think I just set it up and then said, plug it in yourself for my lecture class because I was running at the time.
Yeah.
Get a value.
Not yet. What did you get?
5.6 times 10 to the minus 5. I'm gonna double check that. Seems reasonable. I kept it in variables until the end, so just to make sure I didn't do anything.
Alright, I got 0.0125.
Then I did it completely wrong, probably.
Oh, I forgot to multiply by 3. I got 0.0375.
Still bigger than that one.
Yeah.
Nope, I also made another mistake. This is why you don't try to do it in your head.
This is the.
I got 0.005.
I got 5.65 times 10 to the minus 5.
Yeah, that's right. No, that's what I get for doing it. Like, that's why I don't do things in my head.
Shake me out, boy.
Yeah, I forgot to square it. I forgot to multiply by current.
What happened?
All right, you draw a picture. Draw a cross section because it's easier. Here's my cross section. It's got a radius equal to 4 millimeters. So 4 e to the minus 3. Always convert your units sooner than later. Do not wait to do it. The second you write down that number, and I'm having a hard time fitting it in here, but 4 e to the minus 3 meters. We're trying to find the magnetic field at some point that is I don't have room in there. 1.5 e to the minus 3 meters. Notice I drew my dotted line already because it's Ampere's law. Yay. All right. Integral of b dot dl equals mu naught I enclosed. It's a circle. The shape we chose was a circle. We always choose a circle. So that's 2 pi r, where r is the radius of that fake circle I drew. Mu naught I enclosed. To find I enclosed, we don't have all of it. We don't have none of it. We have some of it. So we're going to do I enclosed over area enclosed equals I total over area total. What's the area of a circle? Pi r squared. So we get I enclosed equals I total times pi little r squared over pi times big R squared. Why? Area total was pi big R squared. Area enclosed was pi little r squared. All right, pi's cancel. It's a ratio of volume or a ratio of areas. Ends up being a ratio of the radii squared. So I total times little r squared over big R squared. So you get B equals mu naught times one of these r's is going to cancel one of these r's. I total times little r over 2 pi big R squared. You plug in the numbers, you get the answer. Yeah, that's all there is to say there. Mu naught is 4 pi times 10 to the minus 7. If you haven't gotten that one memorized yet, you need to solve more problems. Because it shows up in every problem. Like, it'll be on the formula sheet, but... Oh, no. All right. If it's not on the formula sheet, I'll give it to you on the test. That's an interesting point. I didn't realize that. Well, let's see. It should be on the... Okay, if it's on this one, I forgot to put the constants on one of them. I'll fix that later. Yeah. I did add the constants. Yeah, the one I emailed. So I sent it to them. I forgot to put the constants in it, but that was one of the typos I fixed. There's always typos. They didn't notice. Or they might have noticed and just thought I was being mean. That was maybe the case. All right, great. There's the thing. Easy peasy. All right, last major section. Don't worry, we are going to finish early today. We're almost at the end, honestly. This is the last major section we did. We'll talk We'll talk for a tiny bit on inductance, but magnetic flux. We first need to understand that. Faraday's law is what explains how every single generator out there works. Every single way we produce electricity outside of batteries and solar power is explained by Faraday's law. So it's really powerful. It's how we produce electricity, which is wild. And I was able to cover it in a week, kind of. I had to teach you about magnetic fields and a bunch of things. All right, magnetic flux is how many field lines go through a loop. It's integral of B dot dA. It's literally just like counting the number of field lines. You can think of it that way. I spared you all having to do the integral, and I will always give you problems where either the magnetic field does not vary in location. It could vary with time, but I'm not giving you any where the magnetic field varies in location or the area can't vary in location. So, anyway, so all that to say, the flux is always going to be B times A times cosine theta for every problem. When that flux changes with time, we get an EMF. EMF is a fancy word that for all intents and purposes, we're going to treat it like voltage. It acts like voltage. It's not voltage, but it acts like it. Equals N, that's the number of loops that I have, and my change in flux with respect to time. There's 3 variables that can change in flux. B, A, and theta. Make sure you can do every kind of problem. Make sure you can do a problem where B is changing. Make sure you can do a problem where A is changing. Make sure you can do a problem where theta is changing. If V equals IR, then the EMF equals IR. So you can find current really easily. Find the EMF and just divide by resistance. It's a really easy step. But if you haven't done a problem where you've had to do that, and you see that in a test, you will be very confused. Because you'll be like, current? Yeah, anyway. So make sure you've done a problem with that. I told you theta can change. Make sure you all are cool with rotating stuff. Specifically, omega equals delta theta over delta t. So another way of writing this, just to maybe make this a little easier, theta equals WT. And if you're not cool with that expression, if you're like, that doesn't make sense to me, I really hope you're okay with x equals vt. That's from physics 1. That's like constant velocity. It's a really simple expression. This is the exact same equation just for angles. Replace x with theta. Replace velocity with angular velocity. That's what omega stands for. So if you're cool with x equals vt, it's a small step to go to theta equals wt. Why is that useful? Just take that and put it where theta is. And ta-da, you made it a rotating object. Cosine omega t, and then reminder, omega equals 2 pi f. So this is another thing you need to remember. Frequency and angular frequency are not the same thing. Frequency is f. That's frequency. Omega is angular frequency. They have the exact same units, which is a pain in the butt. But angular frequency is the theta or it's the radians per second. Frequency is rotations per second. They represent different things. One's the rate, how many revolutions per second. The other is how many radians per second. And Clearly, mathematically, they're different, so be careful. And then for a sliding rod, there's the equation for it. You're like, what does he mean by a sliding rod? It's this problem, the sliding rod. It's down there. Make sure you all have done a problem on that. I don't have any in here, but okay, great. I got a couple problems for y'all. One's gonna be rotating, one's not gonna be rotating. Let's do the non-rotating one first because it's maybe easier. I don't know. I didn't get to do this one in my first class, so I want you all to try. All right. The radius of some loop changes according to 5t to the 4th. There's no units for distance in there, so that's kind of weird. That's fine. It just spits out meters. It's fine. We'll just say it spits out meters. All right. Find the magnitude and direction of the generated current. Lost a word. When this loop has an area vector pointed in the positive y and a field, it's in the xy plane, but it's 50 degrees above the x-axis. Draw a picture. Draw the loop with the area vector. Draw the field. Then go from there. If your picture is bad, your answer will be bad. Oh, what a nice picture.
I'm trying to like this first, but then I realized it's like the X.
Yeah.
I don't know which one it actually.
No, you're perfect. That's perfect. Yep, perfect. No. I mean, that one might be okay, actually.
Yeah, I mean the angles confuse things.
That picture is much easier to understand, so I just like that one better.
This picture
I was gonna be like,
Oh, there's a reason I told the area vector. Yeah.
I'm no artist.
I hate drawing three-dimensional stuff.
Can't do it. Let's do the math.
So really what I'm looking for in these pictures is the area vector and the magnetic field vector. That's the most important thing in the picture. Anything else is kind of, there's a tiny piece. You need to know it's a circle loop, but.
is that your field?
No,
The
I'm
Joe
trying to
one,
three
my
dimensional
recommendation,
coordinates.
X to the right, make
I
Y up.
failed miserably.
That's the easiest way to do it.
You feeling like it?
No, but it makes me want to sneeze.
Okay.
Yeah, that'll work. That'll totally work. Yep, totally works. Yeah, so you can draw yours however you want, but just this is the coordinate axis I'm going to use. There is a z-axis, but whatever, it doesn't really matter.
Yeah.
Okay. Like in my cosine use 40.
It's good practice to draw three-dimensional stuff. So on that axis, draw your area vector, draw your magnetic field vector, if you choose to use the same coordinate axis that I've drawn up here. And then once you have that, you can do the problem. You don't need to wait on me. All right, so the area vector points up because it says in the positive y. So there's my area vector. Now, to draw my loop, how do you draw a loop that fits this? You draw it so it's going to be flat. As weird as that. Area vector points up. That loop is kind of flat on that weird plane. All right, great. Which way does the magnetic field point? The magnetic field points 50 degrees above the x-axis. So that's 50 degrees. All right. Cool. What are we solving for? Y'all tell me. We will need EMF to find the end goal, which is, I heard someone whisper it off in the distance. current, generated current. So let's find the magnitude and direction of the current. We'll kind of find the direction of current. It'll be fine. That one's going to be a little funky, but it's fine. I'm not too worried about that. I think I don't even know why I have direction. I don't know why I have direction in there. It's going to be kind of jank to find. Whatever. All right. Why is there a current? That's, the next question that should pop into our mind. Why is there a current? Someone already mentioned it. Because there's a change in flux which causes a current. What's in between the two things? An EMF. There's a voltage made. We don't use the word voltage, though, in this case. There's an EMF made. And remember Ohm's law? EMF equals IR. So if I can find the EMF, I divide it by resistance and I get the current. Again, if you haven't done one of these problems, you're probably going to be like, current? I don't know how to find current from you have to just realize to divide by resistance. You have to. How do you know that? You've just done at least one or two of these problems. All right. Why is there an EMF? Someone already said this. There's a changing flux. Now, we'll just write this out again. So negative N, the change in flux, either my B can change, my area can change, or my angle can change. Which one is changing? Is my field, does it say anywhere in this problem the field is changing? No. Is my area changing? Yes, my radius is changing. So therefore my area is changing. Is my angle changing? No. And I'm going to give you all 30 seconds to think about this. What is the angle? The reason I'm giving 30 seconds, I want you to actually think about it. Don't just jump to an answer. Otherwise you have a good chance of getting it wrong. What is the angle in this problem that we're going to use? What angle are we going to use in this equation? Spend 20 seconds actually thinking about it before you respond. All right, what's the angle? It's 40. It's not 50. Just because I give you an angle doesn't mean it's the one used in the equation. The angle is the angle between B and A. That's 40 degrees. If you don't draw the picture, you won't see that. The angle is the angle between B and A. It shows up in the equation right next to them. So we get, and N is 1. There's only one loop, so that's going to go away. So we get negative cosine of 40 degrees, because it's the angle between B and A, times B, which is just B, times the area, which is pi r squared. I'm just going to go ahead and pull out that pi. And so I get D times 5 to the 4th squared dt. Why is it squared? Because r is squared. Whatever happens to r needs to be squared. All right, and you all can kind of work this out of this. Cosine of 40 is not a nice number, so I'm not going to bother with it. It stays cosine of 40. It's the physics way. If it's a gross number, we leave it gross. There's a reason we never write the value of pi in these equations. It's a gross number.
Unless you're an astrophysicist, and that's 3.
Oh, is it? Do y'all do that? Oh, no.
You said it's just 3?
For in astrophysics, when we're talking about stuff that's in arc seconds, that's
okay.
like a pi doesn't.
Okay.
All right, so, 5 squared is 25. Let's just pull that out, too. T to the 4th squared. You all got to remember your power rule. That's t to the 8th. You just multiply them. Unfortunately, and 8 times 25 is going to be 200 times b times pi times 200 times t to the 7th, and that's my not answer. That's not the final answer. There's one last tiny little step. This found EMF. What am I solving for? Current. How do I find current? Divided by R. I'm just going to chuck that up here. So I equals negative cosine of 40. It's not a pleasant number. T to the 7th divided by R. But at least I didn't have to plug in numbers. Whatever. Little gross answer, but the process is what I care about. This is what you get when I make review problems. You get what I throw together. Test problems, I'm much more careful. Yeah. If it's ugly, I don't need you to simplify it. Yeah.
Why is the EMF negative again?
Oh yeah, the negative sign. You can pretend we don't really care about the negative. So this negative just tells it. Okay, so this question said find the direction of it. Question to y'all: does my radius get bigger or smaller? So this is actually a good exercise. If my radius gets bigger, am I getting more field lines or less field lines? Do I want that? No. So which way? So I'm actually going to make a magnetic field the other way. So which way is current going to go to make that happen? The current's going to flow this way. We're going to have some better example problems to practice this. This one was a little messy. The current will flow, if you look at this from above, that's clockwise. If you saw me, I was literally like positioning my head to look at it from above. If it works, it works. Oh, yeah.
Does n become 1 because there's no number of coils?
Yeah, great question. Yep, it's one loop. Yep, it's a loop. If there's coils, I'll tell you there's coils. I'll say there's this many loops. 50, 60, 70, a million. This one has no. All right, great. So that was actually the more complicated one. What's the equation for the EMF made by a square loop with sides L and a magnetic field rotating with a constant frequency of F? This is going to rotate such that it actually makes an EMF. That's an important thing. It's always fun to state. Just spins in a second. Such a pain to write to denote the direction of it. Yeah. There will be an EMF, so it will rotate such that an EMF is generated. So draw a picture that actually rotates the right way. That'll be a test.
Yeah, just replace it.
Yeah. Square. Yeah. And then that's the one. Oh, dude, we have matching pictures.
All right, there's my square. Which way do you all want the magnetic field to be? It doesn't specify. Just pick a direction.
Right.
Sure. Okay, I can do right, but it's gonna make it. That's fine. No, that's fine. We'll have it be to the right. That's fine. It's not a bad thing. It doesn't change anything. If you're like, but there's no field lines going through it right now, that's fine. It's gonna rotate. It'll gain field lines. It will get EMF because it's gonna start to rotate. Now, when I told you it had to rotate to make an EMF, there's two ways I can there's lots of ways I can rotate this. We're going to rotate this like a coin, not like a steering wheel. Steering wheel, nothing would happen. So how are we going to denote that? So we're going to do like this, and it's going to rotate, like a coin. Spinning coin. That's my hand-wavy way to describe it. Okay, great. Now you got a picture. Try it out. Almost there, y'all. Just got a couple more slides after this. Literally 2. Okay, technically there's a 3rd, but that would be quick. 3 more. But they're quick. All right, so I wrote another step up there. I just keep writing the EMF equation again and again. What's changing here? Is my magnetic field changing? No. Is my area changing? No. What is changing? Theta. You need to rewrite theta in terms of a variable given in the problem. There is something given in the problem that gives us the rate of change, not necessarily of theta, but at least of rotation. Theta equals 2 pi ft. Why? Because theta equals omega t. Why? Because of the things I said before. All right, negative n. Hopefully we're all cool if the area is L squared. Derivative of cosine 2 pi ft dt. This is a super easy derivative. Hopefully. If it's not, practice. Negative's going to go away. Not that it really matters. Chain rule. Great. 2 pi f comes out. There's our solution. Now, this gives me the EMF as a function of time. What if I asked you for the maximum EMF? How would you find that from this expression? There is a way to kind of quote unquote derive it. So that's a function for EMF. When is it maximum is one way to think about this. At what time is this maximum? Time is the only thing that changes in this function. Yeah, when time is zero, not quite zero. Sine of 0 would be 0. What's the largest sine can be? 1. Why am I saying all this? So it would be when that inside is kind of gross. It equals pi over 2 or something like that. Anyway, all I need to remind you all of, this is something you all very much need to know, not just for this class, but like any class moving forward. You need to understand how sine functions look like, and specifically that the thing in front of it is the amplitude. Why do I say that? The amplitude is the largest value. So if I said, hey, what's the largest EMF I could possibly get? It's just the term in front. That is the amplitude. All of those are constants. And another way you can think about it, you can quote unquote derive this yourself. When is it maximum? When the sine term equals 1. What happens when that equals 1? You're left with all the rest of the junk. So this is something you do need to understand: sine waves, cosine waves, and what the various terms represent in them. So keep that in mind. Amplitude, i.e. maximum. I.e. max. All right. So great. Last couple things. We're going to do inductors, Lenz's law. This is going to go quick. These are pretty quick and straightforward. Lenz's law. How do you find the direction of current? 3-step process. There is no shortcuts. Draw a picture. Am I getting more or less B, and in what direction? Make a B to counter it. Then use right-hand rule 2.5 to find the direction of current induced if any is induced at all. So my first picture, I got something spinning like a coin. It's in a magnetic field pointed into the page. As it spins, do I get more dots or less dots? Less. And if it's dots, what does that represent? What direction? Out or in? Fantastic. I'm getting less out. I don't like that. How do I counteract that? Yep. Make B out. How do I make B out? Thumb out. Fingers curl. I'm going to need to make more B out. That's going to make a counterclockwise current. Great. Y'all got a minute to do the next one. I got a bar sliding upwards. Am I getting more or less field lines in which direction? Counteract the change. Make the current. Yeah, always. Yeah, we don't care about the outside. Give me long time to make dots and X's. I had to make those. Oh, they're individual X's distributed. You just make a few of them.
Copy paste them.
Oh yeah.
Crazy.
Oh, most diagrams you see, I had to make through just.
I'm surprised there isn't just like PNG that's just dots.
I'm sure, but then just have max control over the size.
Yeah, that's
And if the ones you find, they're not going to be SVGs. So if they're PNGs and you stretch them or squish them, they look ugly. All right. When the bar moves up a little bit later, did I get more X's or less X's inside my loop? Less. So I got less B in. I don't like that. What do I do? Make B in. How do I make more B in? I'm going to make a clockwise current. Make sure you all can do this. All right, inductors. There's some equations for them. What is an inductor? It's a solenoid. What does a solenoid do? It resists a change in current. Why does it resist a change in current? Because of everything we just covered. As a current is generated, it makes a field. It doesn't want a field, so it fights it. It fights itself. It fights the other coils inside of itself. We derive the inductance of a solenoid. There's the equation for it. Mu naught n squared A over L, or mu naught lowercase n squared A times L. Only one of those is given. You just need to remember that lowercase n is capital N over L. I do not have any questions about the energy stored in the solenoid, but there it is for funsies, 1/2 Li squared. It kind of looks like the energy stored in a capacitor, 1/2 QV squared, just different variables. It's coincidental. And you all need to remember when inductors resist current the most. Specifically, we did the quicker questions on this. When did it resist it the most? When switch S1 was closed, because that was the biggest change in current. It hated that. As time goes to infinity, eventually it stops carrying. The change in current becomes 0 and it stops carrying. So, try these next two problems. These are the last two problems, and then we've covered everything. 5 weeks of content in 2 hours. It's a marathon, y'all. So what happens to the inductance if I use 3 times the current, half the radius, and quadruple the length of my solenoid?
Oh, really?
I think there's a question.
Yeah, so like,
I'm sitting here like, what is going
There's
on?
no line equation.
Yes.
Point your thumb in the direction of the field you want. Which way do I want to be? Yep. I want to make it, and I want to
I was thinking about
focus on the
Yeah, I was like, am I looking at the right equations?
so it's makes the end. So don't put it understand. That's it? Yeah. So that's nice.
So that's well instead of something more confident.
Yeah.
And even if you're not like,
I doubt myself a lot, and that kills me. That has killed me.
yeah,
I've learned to try a little more. Yeah, but
I have to trust myself.
too much doubt kills me.
All right. Y'all got 2 equations you can use for inductance. One is good, one is bad. I got 2 equations here. The key here is you don't want to use the second one. You'll get the wrong answer. Why don't I want to use the second one? That lowercase n has an L inside of it. That lowercase, and you can see that if you do the other one. This n here is capital N over L. There's an L hidden inside of it. So you don't want to use that one because as L changes, lowercase n changes. My capital N does not change. So we're going to use the left side one. So this is my original. My new is going to be mu naught times n squared. If I use half the radius, the area is pi r squared. I'm going to write that over here, pi r squared, so that I don't need to write this. If my radius halves, you better square that. Don't forget to do that. If I quadruple the length, then you better quadruple the length. If I triple the current, I don't care. It doesn't show up in the equation. All right, so my new inductance, r over 2 squared, that's r over 4, so that's going to pull out a 1/4. I then pull out another 1/4 from the bottom, and I'm left over with mu naught n squared pi r squared over L, which is 1/16 the OG. So yeah, this just comes down to plugging it in. Be careful. If something's squared, you better square what's happening to it. Awesome. All right, in the bottom, when I close switch S1, what happens as t goes to infinity? When I first close it, I get a really big change in current, and it hates that. So the best way to understand this is there's a graph I gave you all that this is what my current looks like with respect to time. So as time goes on, that rate of change of current, eventually I will reach a maximum current. Eventually I'll reach a maximum current. What is the slope of that line? When t goes to infinity, what's the slope of a flat line? Someone did say it, but it wasn't very confident, so I want to... 0, great. So what's the EMF? The back EMF made by an inductor is L di dt. If di dt is 0, what's the EMF, the back EMF generated? The inductor's doing jack squat. Why does that matter? Okay, the inductor basically is a wire. As time goes to infinity, the inductor turns into a wire. I have a battery, a resistor, and a wire. How do I find the current when there's a battery and a resistor? V equals IR. There you go. This is to show you all we did when time equals 0. We did that problem in class. That was when it changed the most. And in this case, it's just showing you the inductor turns into a wire at some point. It doesn't do anything. Now, if I then open that, if I tried to change the current, it would start carrying again. All right, that's it, y'all. Rest your brain a bit. Make sure any problem in this today that was complicated, find examples of it to practice. That's the purpose of the review, is not to teach you all the things, but to help you identify what's hard. That's the stuff you should practice. I'll post these immediately.